Hello, my dear friends. I'm Shubham from LearnoHub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnohub.com. So then, let's start. So as you all know, friends, we are going to study in this video your class 10th ICSE chemistry chapter number 8 part B, ammonia, right? Study of compounds, and in that we are going to study the second compound. We have completed the first compound, hydrogen chloride, okay, in the first video, okay, of this chapter. Now in this video, the second video, we are going to complete the ammonia, okay. We are going to study the concepts of the compound ammonia, right, which is given in your syllabus. So I'm strictly going to stick to your syllabus, okay, not beyond anything from your syllabus I'm going to teach in this video. And also lastly, we are going to solve some questions which have been asked from your previous year exam, so that you would get an idea of how questions are being asked, right? So then, without wasting much time, let's start and let's rock. So as usual, starting from the first and the very important question before starting to study the chapter, that why we should study this chapter, why we should study this compound ammonia. Okay, so there are so many interesting examples, as I have stated on this slide. It is used as a refrigerant, okay. It is also used, right, we have studied this application. Its aqueous solution is used for detecting the metal ions, right, in the analytical chemistry I have explained it in detail. So that application is also there in lab, okay. It is also used for preparation of nitrogenous fertilizers, and the main one is urea, right, very important. Also it is used for preparation of sodium carbonate, okay. By Solvay process we use ammonia there. No need to go into details of that. I'm just giving you the uses, okay, so that you could get an idea that how variety of uses it has. And lastly, okay, the dangerous use, that is, it is used in the manufacturing of explosives, okay. Boom. So like for example, ammonium nitrate, okay. So this is the ammonium salt, so it is used for the preparation of this ammonium salt, and which is used as explosive. So looking at this uses, you would have figured out that it has a variety of uses, right from the very good uses to us, very important uses to us, to the uses which are not very much useful or which are dangerous to us, right? So I hope you would have you are now feeling convinced of studying this compound. So then let's start. Okay, so now I have divided this chapter into into two main topics. Okay, so if you would see the syllabus, you would find so many topics, but I have just made it simpler for you. Okay, first is preparation. We have to study the preparation of ammonia by various methods, and second one is properties. So we have to study its physical properties, some physical properties, okay, and some chemical properties. So in preparation, we are going to see these four methods of preparation. First is the lab preparation of ammonia from ammonium chloride. Second one is from ammonium salts, okay, by using alkalis, and then third one is from metal nitrides. Don't worry, we are going to see all these things in very much detail. So from metal nitrides using warm water, and last one is the well known, if you haven't heard about this word, Haber's process. So don't worry, it's very interesting process, okay, for production of ammonia. So we are going to see these four methods of preparation, and then in properties, physical properties, we are going to see two physical properties, density and solubility. And for solubility, we are having the fountain experiment, same like that of the hydrogen chloride, okay, to demonstrate its solubility. Lastly, the chemical properties, okay, but the chemical properties are too interesting. First one is burning of ammonia in oxygen, okay, how it burns, then catalytic oxidation of ammonia, then ammonia as a reducing agent. So we will see some reactions here as well, okay, and the reactions of aqueous solution of ammonia, that is ammonium hydroxide. So reactions of ammonium hydroxide with acids, with the soluble salts, okay, soluble metallic salt solutions. We are going to see all those things, okay, in very much detail as well. So I hope you would have got a glimpse of what we are going to study in this chapter. So then let's start with the first one. Okay, so now let's start with this lab preparation of ammonia gas, right, from ammonium chloride. Okay, so in this we are going to set up the apparatus first, okay. So you feel like we are going to do this experiment, so that you would be able to understand this experiment, okay, very nicely. You would be able to understand this lab preparation very nicely, so that any conceptual question which would be asked from this topic in your exams, you would be able to answer it very easily, okay. So now what I have done is I have taken a round bottom flask, as you can see here. I have just tilted it, okay. Why we should tilt, I will tell you, okay. Lastly, I will tell you in the precautions why we should use this flask in the tilted manner. But for now, you just remember, or you just let it be in this tilted way, this round bottom flask. And then I'm going to add calcium hydroxide and ammonium chloride, okay. And this calcium hydroxide I'm going to add in excess, okay. And both of them, ammonium chloride and this calcium hydroxide, which is in excess, I'm going to grind it. Okay, so fine powder I'm going to add. Okay, of both. Okay, finely grinded. And what I'm going to do is, okay, now in the procedure I will tell you later, but for now how we are setting the apparatus, that I have told you. So in the flask I am taking this, okay, excess of calcium hydroxide and ammonium chloride, okay, finely grinded, finely divided, and then I'm going to put a rubber cork here. From this rubber cork I'm going to pass a delivery tube which would start from here, okay, from the mouth of this round bottom flask, and then it would enter this drying tower. Okay, and in this drying tower I have kept this quicklime. Okay, what's the use of it, I will tell you later, but I have kept this quicklime, and then from this drying tower I have also fixed a rubber cork. I have just attached this delivery tube which is ending up in this inverted glass jar. Okay, this is the inverted glass jar. Very nice, very clear, understood. Now this is all about how we are going to set up the apparatus, and also we need a Bunsen burner to heat the mixture. Clear? Okay, so now we have now setted the apparatus. Now in the procedure, simply we have already taken excess of, right, calcium hydroxide and ammonium chloride. Okay, just excess of calcium hydroxide, okay, not excess of ammonium chloride. Only we are taking calcium hydroxide in excess, ammonium chloride in normal amounts, and we have finely grinded it before taking it, and we are now, what we are going to do is, simply the procedure is we are going to heat it. That's it. So this calcium hydroxide which is in excess is going to react with our ammonium chloride. So in order to understand how the ammonia gas is going to be formed, first we will need to understand how the reaction is taking place. Once you know the reaction, it would be very easy for you to understand the process. So excess of calcium hydroxide, right? So I am writing here calcium hydroxide in excess. Okay, this is the reactant, one reactant, and then ammonium chloride. So ammonium chloride, right? Then we are heating the mixture. See, the chemical equation just becomes like this. If you understand the process, you could write the chemical reaction very easily. So reactants, then this is the condition, we are going to heat the mixture, right? And what we get is, we get calcium chloride, okay, a salt of calcium, and then along with it we get ammonia and water, okay, as a gift. So ammonia we need it, okay, and we get water as well. So these are the three products. Now out of this we are only interested with this ammonia, right, because this is the lab preparation of ammonia. So this ammonia gas is released, and now this gas is allowed to pass through this delivery tube and it reaches this drying tower. Very simple. Now what we are going to do is, we are just going to dry the ammonia gas, right? Now here in this drying tower I have already placed the quicklime here, calcium oxide, which is a drying agent. Okay, now this quicklime dries our ammonia. So when ammonia passes through it, ammonia gets dried. Now just a point to be noted here, that we are using as a drying agent as quicklime, calcium oxide, but we don't use the drying agents like P2O5, right, this phosphorus pentoxide, okay, or we don't use concentrated sulfuric acid, which we have used in the case of HCl gas, right, or we also don't use anhydrous, okay, calcium chloride as well. Okay, so all these three we don't use as a drying agent here, we only use calcium oxide. Now why we don't use them? Okay, the simple reason is, all of them, okay, react with our ammonia, okay, and we don't want any of this to react with ammonia, because our primary aim is to just dry ammonia, not to carry out a reaction of this with ammonia, right? So in order to avoid this, okay, we always want to avoid the reaction, that's why we don't use this, we only use this calcium oxide, right? Very interesting. Okay, so far we have dried the ammonia gas, correct? This point we have reached, till this point. Now the last step of this process, of this lab preparation, very easy preparation, is just we have to collect the ammonia gas. Okay, so the dried ammonia gas, then I would allow it to pass through this delivery tube, and then I am taking this glass jar, but I have kept this glass jar in the inverted manner, okay, ulta. So why I am doing like this? Because see, ammonia gas goes into this glass jar, but already there is some air in this glass jar, correct? But what happens is, ammonia, okay, it starts to get collected at the top of the glass jar in this way, pushing out the air, okay. So how is the method of collection of ammonia? downward displacement of air. Okay, right? Downward displacement of air. The air is getting displaced downward, or we can say upward delivery. Okay, the ammonia gas is delivered, okay, on the upper side, right? It is staying in the upper side, so upward delivery. Now, why is this so? Why there is a downward displacement of air when we collect the ammonia, okay, or why the ammonia is being collected by the upward delivery? This is simply because ammonia is lighter than air, okay. So if it is lighter than air, we know that already there is some air here, okay, ammonia gas is going inside here. So since it is lighter than air, it would be placed in a layer above the air, okay. So more and more ammonia gas is getting formed, so air would get lower and lower, because the layer of ammonia gas would increase, right? Ammonia gas is going upper and upper, right? It is getting settled in the upper layer because it is lighter than air, so it is settling down, okay. It is settling in this way. So ultimately when the glass jar, okay, becomes full, it would be full of ammonia gas. All the air would be out of this gas, out of this inverted glass jar. So in this way we collect ammonia, since it is lighter than air, okay. If we would use the same method, okay, of the collection as that of the HCl, okay, try to recollect how we just collect the HCl. It is by the upward displacement of air. Now why was it so? Because HCl was heavier than air. So when we were allowing the delivery tube to enter into the glass jar, okay, HCl was heavier, so it was settling down, and that's why the air was displaced outside the jar. So we were saying that it was upward displacement. Here it is downward displacement. So very interesting phenomena. Okay, see both the gases, okay, HCl and ammonia, but yeah, it has some different behavior. Just because the difference in their density, means just because their lightness or heaviness as compared to the air. Okay, since ammonia is lighter than the air, it is collected by the downward delivery, or by the downward displacement of air, or by the upward delivery. Okay, so I have told you how to remember this collection method. Now apart from it, also one interesting thing you have to study in the syllabus is identification or test. So how you would identify that whatever gas is produced in this process, it is definitely ammonia. So first of all, ammonia is having a very sharp characteristic odor. Okay, so if I would also suggest you, okay, to have just a glimpse of its odor, okay, just a slight glimpse. Don't take the odor too much, okay, it's not good. So it has a very sharp characteristic odor, okay. Another thing is, since it is basic in nature, so what happens is this ammonia gas, okay, if I would insert moist red litmus paper, okay, so since it is basic, what it would do is, we know it would turn the red litmus paper, the moist red litmus paper, blue, right? Because bases turn blue. I have told you the trick in acids, bases and salts chapter. So this is also a very interesting test we can use to detect whether yes, it is ammonia or not, to confirm it is ammonia or not. And the another one which we have already also studied it, that what we can do is we can take ammonia gas, okay, this, and then we can add concentrated HCl into it, okay, in the ammonia gas. So we would observe ammonium chloride, okay, and we would observe ammonium chloride, but how we would observe? We know it gives off dense white fumes, okay, and these dense white fumes are of ammonium chloride. Very clear? Very interesting. So this we have already studied, just we are here using the concentrated HCl part. Otherwise we have studied ammonia gas is reacting with HCl gas, and we are getting a product by reaction of these two gases, which is solid, that is ammonium chloride, which is also dense white fumes. Okay, so I have told you in a starting point of this lab prep that I will tell you about the precaution why we are using this round bottom flask, okay, in this slanting position. So the interesting thing here is, we know that after the reaction between this excess of calcium hydroxide and ammonium chloride, okay, when we heat them, we get ammonia, calcium chloride and water, right? So this ammonia gas passes through this tube, okay, calcium chloride may remain here itself, but water is also there, right? And we don't want our water, okay, which is like we are heating here, so water vapors would go up and then again they would condense and come back and fall on the glass. So we don't want our water to come back and fall on the glass here, on the round bottom flask, because it is hot here. So if that water falls on this glass, it would break this round bottom flask. So to avoid the backfall of water into the flask, okay, which would result into the breaking of the flask, we place this round bottom flask in the slant position, so that the water whichever water is produced, it just accumulates here. It doesn't go back here to the flask, resulting into the breakage. Clear? Very interesting part. And one more thing, okay, I have told you about the precaution here. Slant position of the flask. And one more thing is, very interesting point about calcium hydroxide. We are using it in excess, but why we are using calcium hydroxide, not any other alkali like sodium hydroxide? Okay, because calcium hydroxide is basically very cheap, first of all. Okay, just like we have used sodium chloride for the preparation of hydrogen chloride gas, in the same way we are using calcium hydroxide because it is cheap. That point was also for sodium chloride we were using for preparation of hydrogen chloride because it was also cheap, right? So here it is also cheap. That's why we are using it. First point. And next one is, okay, it is not deliquescent. Okay, so deliquescent. Okay, it is not deliquescent. Okay, SCENT, QUESCENT. So since it is not deliquescent, now what's the meaning of deliquescent material or deliquescent substance? Means if we keep this calcium hydroxide as it is in the air, so it would absorb the moisture from the air. Okay, so water vapors from the air would be absorbed by the deliquescent substance. Okay, and then that deliquescent substance would dissolve in it. For example, sodium hydroxide. Okay, this is a deliquescent substance, so it absorbs the moisture from the air. Okay, and then the solid sodium hydroxide pellets starts to dissolve in that moisture. Okay, starts to dissolve after absorbing the moisture. Clear? So you would observe the pellets of sodium hydroxide starting to get means like starting to dissolve. Okay, converting into the liquid NaOH. Right? Very interesting phenomena. So, but this doesn't show deliquescence. That's why we are using calcium hydroxide. Okay, because we don't want deliquescence, we want our calcium hydroxide to react with ammonium chloride. So these were the two things which were interesting about the calcium hydroxide, about this lab preparation of ammonia. Okay, now let's see the preparation of ammonia gas from ammonium salts using alkalis. So I have deliberately taken this method after the lab preparation because it is exactly or almost same that of the lab preparation. See, in the lab preparation also we have used ammonium salt. Which is the ammonium salt? Ammonium chloride, right? And also we have used alkali, right? Calcium hydroxide, correct? So here itself also, okay, the same type of preparation is there, okay, in your syllabus, but I will tell you some few more things about the use of ammonium salts for preparation of ammonia. Okay, so firstly, basically the reaction remains the same. We are taking ammonium salt, okay, and then we are taking alkali, we are heating it, okay, simply, and we are getting the salt. Here now it would be calcium chloride, okay, because here with ammonia there is chlorine, so calcium chloride would be the salt, ammonia and water would be the products. Okay, you balance the reactions on your own. I'm not writing the right balanced equations, okay, because we are not wasting our time in balancing the equations. It's very simple. You know how to balance the things, okay, balance the equations. Okay, we have studied in the previous standards as well. So this is the simple reaction. Okay, like this you can also write some other reactions as well, like for example, for ammonium sulfate, NH4 twice SO4, okay, SO4 2 minus, that's why NH4 would be required, means NH4 would be required 2 NH4 because NH4 is plus, so 2 plus, right, 2 minus, so NH4 twice SO4, right? NH4 twice SO4 would be the formula for ammonium sulfate. Now if I'm using again calcium hydroxide itself, okay, I'm heating it, what would be formed? Calcium sulfate would be formed, right? And then ammonia and water, simply calcium sulfate, ammonia and water. So now in this reaction we can use, for the alkalis we can use calcium hydroxide, as you can see here, we can use sodium hydroxide, okay, we can use potassium hydroxide, right? These three alkalis we can use. Okay, now regarding the ammonium salts, the interesting thing is we cannot use, okay, though all the ammonium salts, okay, give us ammonia on heating with, right, heating with alkalis, okay, but there are some ammonium salts like ammonium nitrate. Okay, now I have told you about this salt. This is explosive, right? We have seen in the uses. So this ammonium nitrate and ammonium nitrite, okay, both of them, they don't give us ammonia when we heat them with the alkalis. Now why is this so? Because when we heat them, okay, they themselves, okay, get decomposed, right? So if they are getting decomposed, then they are not remaining in the form of these salts, then how they can react with our alkalis, right, to form ammonia gas. So that's the reason when we heat them, they get decomposed. That's why we cannot use them for preparation of ammonia through this method, okay, by using alkalis. Clear? Very, very interesting. Okay, now the third preparation method, okay, by using metal nitrides, okay, and this metal nitrides we are going to treat it with warm water. So metal nitrides, in this we are going to see only two examples, this Mg3N2, okay, magnesium nitride. So how it would form, right, Mg2 plus and nitride, in nitride N3 minus, okay, so 2 3s are 6 minus, 3 2s are 6 plus, right, so Mg3N2. How I figured out the formula, I hope you would have understood, Mg3N2, okay. Apart from this, we are also going to see aluminium nitrides reaction with warm water. So yes, this is very important. Water we are using, but it is warm, okay, very important condition you need to remember, you need to keep it in your brain, okay. Now when they react with warm water, very simple reaction, okay, we know the product would be obviously ammonia, right, because here we are studying the methods of preparation of ammonia. So you have to just use your brains, right. It would definitely give us ammonia, and also along with ammonia, now see, it gives us hydroxides. Okay, so see, this nitrogen is involved with the hydrogen and forming ammonia. So remaining metal, oxygen and hydrogen are forming hydroxides. Okay, so here it would be magnesium hydroxide. Now how to write the formula? We know that here in this compound Mg3N2 magnesium nitride, Mg is in +2 state, right? So +2, it is having charge. So this +2 Mg would combine with, for forming hydroxide, it would combine with OH minus, hydroxide ion. So how many hydroxide ions? 2 hydroxide ions would be required, because it would become 2 minus. Here it is 2 plus, then 2 minus, right? So Mg2 plus 2 OH minus, right? So MgOH twice. In this way you have to write the formula. Okay, along like this only. Here see, aluminium nitride, because nitride 3 minus, aluminium 3 plus, right? So aluminium nitride is fine. Then what is forming? Ammonia is forming, and then aluminium hydroxide would be formed. So what would be the formula for aluminium hydroxide? Aluminium, here it is in 3 plus, right, charge. So 3 plus would require 3 minus. So 1 OH is having only 1 minus, right? So I would require 3 OH minus, right? So 3 plus, 3 minus. So AlOH thrice. In this way you have to write the compound's name. Okay. So if you just remember the word reaction, okay, that is simply the nitrides when react with warm water, okay, they give us ammonia and hydroxides. That's it. Our job is done. Nitrides with warm water gives us ammonia and hydroxide. Then you can write the reaction, okay, on your own as well. Clear? Very interesting, very simple. Now friends, coming to the very interesting process of formation of ammonia, okay, or manufacture of ammonia. This is the industrial method, okay. Okay, in industries we use Haber's process for preparation of ammonia gas. Okay, so now what are the reactants which we are going to use in this process? We are going to start from this. Okay, finally in this process we are going to produce ammonia, but we are going to store the ammonia in some different form. I will tell you later. Okay, but for now let's start first with the reactants. What reactants we are going to use? Very simple reactants. First of all, we are going to use nitrogen and hydrogen gases, okay, right? And we are going to use 1 volume of nitrogen and 3 volumes of hydrogen. Okay, very specific. You would come to know this thing from the reaction itself. Okay, now another interesting thing, the source of nitrogen. So we are going to obtain the nitrogen by doing fractional distillation of liquid air. Okay, liquid air. And for hydrogen, we can obtain the hydrogen from water gas. Okay, firstly. Now what is this water gas? Let me tell you. This is the mixture of carbon monoxide and hydrogen, okay, H2. And yes, we are obtaining hydrogen from this water gas, and it is known as Bosch process. Okay, so just for your info, okay, you can also remember this thing. It would be beneficial if some question is being asked from this point. Or else we can generate the hydrogen from natural gas as well. Okay, fine, done with the sources. Now coming to the conditions. So yes, here in Haber's process we have a set of conditions. You need to remember it. The conditions are very interesting and very logical as well. You would remember it in the course when we are going to see this process. Okay, so first of all, very important, temperature first. So temperature is like huge, 450 to 500 degrees Celsius we maintain the temperature. Okay, this is the optimum range. then coming back to pressure. Okay, what else it would be? Okay, after temperature it would be pressure. So pressure is above 200 atmosphere. Okay, so huge pressure is also required for this formation. Then catalyst is also required. So you would say, my god, this reaction is like, it has so much requirements, right? And catalyst, in the catalyst we need iron, but this iron we use it, okay, how? We finely divide the iron and we use this finely divided iron as catalyst. Okay, now finely divided iron, okay, this fine, we are dividing it very finely. This is actually increasing the efficiency of the catalyst. Okay, now I don't need to tell you what is the function of the catalyst. If you would have heard it, if you would have understood it from the bio part as well. Okay, catalyst is simply a substance which just speeds up the reaction, okay, without taking part in the reaction. Okay, it doesn't take part in the reaction, but it speeds up the reaction, right? Very simple. Now along with the catalyst we also use a promoter here. Okay, now promoter, as promoter we use alumina. Now we have studied about it a lot, aluminium oxide, or we can use traces of molybdenum. Okay, you would be knowing this, you would have heard somewhere, molybdenum is an element, right? So this also helps us to increase the efficiency of the catalyst, the promoter, use of promoter as well. So I have told you the significance of finely divide, why we finely divide the catalyst, okay, and why we use the promoter as well. Now apart from this, let's understand the reaction now. What is actually happening with this N2 and H2, and then in this Haber's process, how actually this reaction is taking place. I will tell you step by step how these conditions are useful for us, okay, how these conditions are used in the process. So for that, first understand the reaction. We are taking N2, okay, 1 volume of N2 and 3 volumes of H2, so N2 plus 3H2. okay, now this is a reversible reaction, mind it, okay, this is reversible reaction first of all. Now secondly, okay, it is giving us 2 volumes of ammonia, 2 NH3, so you can just balance it, N2, Cn2, and then 3 to the 6H, so 3 to the 6H. Okay, now along with this, along with the ammonia formation, okay, it is giving us heat. Okay, so that means this reaction is exothermic as well, right? And thirdly, you can observe here there is 1 volume of nitrogen, 3 volumes of hydrogen. So total there are 4 volumes, okay, in reactants, and in products we are getting 2 volumes of ammonia. So in products we are getting 2 volumes. So from 4 volumes to 2 volumes, this means that, okay, the transition is taking place. This means that the reaction is accompanying with a decrease in volume, right? Decrease in volume. You can say whatever you want. So this is the characteristic feature of the reaction. You can write in front on the arrow above the reaction these conditions as well. Okay, 450 to 500 degrees Celsius, above 200 atmosphere, iron finely divided, and alumina or traces of molybdenum. But that would be a huge amount of information on these arrows. So in exams, if they ask you to write along with the conditions, you can write the reaction, okay, along with the conditions. Okay, whichever condition they are asking you, specify that condition. Otherwise, if they don't specify the condition, you just mention all these conditions on these arrow, okay, because you don't, means I hope we all don't want to lose our marks because of some silly thing. We know the things, but we haven't written it. Okay, so this is the reaction. So friends, now I'm going to tell you the process. Now see, in your exams, you know the paper pattern is how the questions are asked. They are all 1 marker or 1-liner answers, right? So they won't ask you, most probably they won't ask you the entire process, right? The process of Haber's process for 5 marks, and all those questions don't come in your exams. Okay, so but we should know the process, okay, because if at all such type of question comes, you are now prepared. Okay, but most probably such questions don't come. But if you are knowing the concept, you would be able to write the process as well, and you would be also able to give the, or you would also be able to write the answers of such questions which are conceptually based on the process, okay, for the Haber's process. So very simple, I am going to use the diagram to make you understand. Okay, this diagram itself is very much self-explanatory for understanding the process. So what I'm going to do is, here I'm going to take nitrogen, okay, 1 volume, we have just seen, okay, in this previous slide, nitrogen 1 volume, and hydrogen 3 volumes, okay. But the important thing here is, first of all, we are going to use this dry nitrogen and dry hydrogen for sure, and we are going to purify it. Okay, now here the purification is important. Why is it important? Because see, this gases may have some impurities like carbon dioxide, carbon monoxide, or it may have hydrogen sulfide. And these impurities, okay, what they would do is, we are using catalyst in this reaction, so they would poison the catalyst. Okay, so we don't want our catalyst to get poisoned by these impurities. So that's the reason we are purifying this N2NH2 before using it. Okay, now it's fine. Chalo, we have purified it, we have dried it, now we are using it. Let's move ahead. So I have made them to enter through these tubes, and then they are getting mixed here, and then I'm making them pass through this compressor. Okay, the second step. So in this compressor, the pressure is very high, about 200 atmosphere. Okay, pressure is around 200 atmosphere in this compressor, and the nitrogen and hydrogen mixture is getting compressed here. Okay, now after getting compressed here, okay, we are making this mixture, okay, the unreacted nitrogen and hydrogen mixture, to pass through and enter this catalytic chamber. Okay, this one, this part. Now, very interesting thing is, this catalytic chamber, okay, is electrically heated. Okay, so by using electricity, we heat it. Clear? Now, this catalytic chamber also has what all things it has, since the name is catalytic chamber, so it definitely has, first of all, catalyst. Okay, so we know which catalyst it has: finely divided iron. I'm not writing it again. It also has our promoter, alumina or traces of molybdenum, right? And here in this catalytic chamber, the temperature is maintained about 500 degrees Celsius, around 500 degrees Celsius here. And here in this catalytic chamber, the reaction between N2 and H2 takes place and ammonia is formed. Just we have seen the reaction in the previous slide. Okay, N2 and H2 react and ammonia is formed. Okay, now I'm not balancing it. Along with ammonia, okay, here heat is also produced. We know that thing. Now let's talk about this heat later on. I will tell you the importance of this heat. But for now, ammonia is produced. But the very poor thing about this process is, okay, now we have passed the N2 and H2 for one time, right, through this catalytic chamber. But out of 100%, okay, only 15% of N2 and H2, okay, the reacting gases, are converted into ammonia. Okay, only 15%, very poor. So what we do is, the rest 85% of N2 and H2 gases, okay, are still there along with the ammonia which is produced. So what our brain suggests is, we won't make this remaining 85% of N2 and H2 as a waste, right? So what we do is, I will tell you, but first what we are doing is, we are just separating this 85% of N2 and H2, okay, from ammonia. Now how we are separating it? See, we are going to pass this mixture of ammonia and unreacted N2 and H2 gases through this cooling chamber. You can see here, this is the cooling chamber. Okay, right, in this cooling chamber, we are passing the cooling liquid in through this inlet. Okay, this cooling liquid is what it is doing? It is actually cooling this cooling pipes, right? This cooling pipes, it is cooling them. Why? Because we are going to pass our mixture through this cooling pipes. Okay, and then this cooling liquid comes out. So whatever heat transfer would take place here, since we know that this mixture, right, N2 and H2 along with ammonia, okay, is like at very high temperature, 500 degrees Celsius. So what we are doing is, here we are cooling it. So the heat from this mixture, okay, so whatever heat would be remaining, okay, when it enters here, it would be dissipated out into this cooling liquid, and this cooling liquid would take out this heat, okay, and in turn it would cool the mixture of N2, H2 and ammonia. Okay, but since we develop such conditions that our ammonia gets liquefied, okay, also very interesting thing to note here is, ammonia gets liquefied much more easily, okay, more easily than N2 and H2. So we take advantage of this property of ammonia, okay, and what we do is, we liquefy ammonia, because we know that it would get liquefied more easily than N2 and H2. Then N2 and H2 would remain in gaseous phase only, okay. So at some lower temperature, ammonia gets liquefied, okay, leaving behind, means leaving in the N2 and H2 in the gaseous state itself. So these N2 and H2 are there in this cooling pipes, okay, and our liquefied ammonia, okay, here we remove it, right? So we got our liquefied ammonia. But this is just a single passage of N2 and H2 which has taken place. But now the remaining N2 and H2 gases, okay, in these cooling pipes, which is not liquefied, right, because they are not getting liquefied easily, so they remain in the gaseous state. What we do is we just allow them to get recirculated, see, in this way, okay, and pass them again through the compressor so that they again get compressed, and then again make them enter the catalytic chamber, okay, so that again the unreacted N2 and H2 would react, they would form ammonia, and again the same process is repeated. They are again passed through the cooling chamber, again unreacted ammonia, unreacted nitrogen and hydrogen are passed, and this process continues and continues, okay, and 98% of N2 and H2 are then converted, okay, by this recirculation method. So we are not allowing our N2 and H2 to get waste, right? Now I have already told you the liquid ammonia, we are collecting it, okay, which is coming out, and we are also storing this ammonia, okay, as a liquid itself, okay, as a liquid, but we are storing it under pressure, okay, under pressure. So this is liquid, but we are putting up the pressure above it so that it remains in the liquid state. So we are storing this ammonia as a liquid under pressure. Once we remove the pressure, the ammonia would convert into gas. Clear with this point? Okay. The last point was this thing. Now let me tell you some interesting thing about the temperature, okay. Now here we know that the optimum temperature range is 450 to 500 degrees Celsius, right? But let me tell you that we only heat the reaction mixture, okay, or the reacting gases, that is N2 and H2, okay, when they are passed through the catalytic chamber for first time, okay, we only heat them when they are passed for first time, okay. Why? Because once they are heated, we know that this N2 and H2, okay, give us ammonia, and along with ammonia there is generation of heat because the reaction is exothermic, I have told you earlier. So once we have heated them, okay, the ammonia is formed, along with it the heat is generated, and then we don't heat again the N2 and H2, okay, then the incoming N2 and H2 is not heated again. Why? Okay, the N2 and H2 which is getting which is entering into the catalytic chamber after this N2 and H2 is getting reacted, more and more N2 and H2 are continuously passed, right? But we don't heat them again. Once we have heated, we just stop heating, because once ammonia is formed, we know heat is generated, and this heat itself is used for maintaining the temperature of this 450 to 500 degrees Celsius in the catalytic chamber, okay, because in this chamber we know that once this ammonia is formed, heat is generated, and this heat generated is used for maintaining the temperature here, okay, in the range of 450 to 500 degrees Celsius. So very interesting, right? We don't heat it again, right? So our energy is not wasted, our energy is saved. And regarding the pressure, we use very high pressure here in this process, okay, but the reason for the high pressure is related to the La Chatelier's principle, okay, and no need to get into details of this principle, okay, right now. Here at this level you would study definitely this La Chatelier's principle, very important in your higher classes in equilibrium and all those things, okay. So now we are done with the preparation of ammonia. We have seen 4 methods by which we can prepare ammonia. Now moving on to the properties of ammonia. So starting with first physical properties. So we have to only study 2 physical properties, just simply density and solubility, okay. Out of that, density we have already studied it from the lab preparation of ammonia by using ammonium chloride. I have already told you that ammonia is lighter than air, right? That's why it is displacing the air downwards, right? Or we are collecting it through upward delivery. This means that simply ammonia is less denser than air, okay. So density of ammonia, okay, ammonia is less denser than air, okay. Now moving on to the solubility. So see, one interesting thing about the solubility of ammonia is that it is exactly matching with the, means it is like matching with the hydrogen chloride gas, okay. Ammonia is also very much soluble, okay, in water. That's the reason we don't collect ammonia gas also over the water. Just like we don't collect hydrogen gas over the water, we don't collect ammonia gas also over the water. Okay. Now, in order to understand its solubility, we are again going to see the fountain experiment, just the same way like that it was done for the hydrogen chloride gas. We have already studied this fountain experiment. So exactly the same setting of apparatus would be there. Okay, like I'm taking inverted, means I'm taking a round bottom flask, I'm placing it in the inverted position, I'm fixing it, okay, onto the stand. Then I'm having a cork, I'm having two holes in this rubber cork. Okay, from one hole I'm passing the jet tube, which is directly entering into the litmus solution, which is red now. Okay, so in case of HCl, it was blue litmus solution. Why we have used red? You would get to know on your own after some minutes, after few minutes. Okay, so we are placing this jet tube in this red litmus solution. Okay, the one end, other end is being kept open at the inside the flask, and the another hole which is there in this rubber cork, we have inserted the dropper in it. Okay, now this dropper is having some water also in it. This is all about the setting of apparatus. Then the procedure is simply we are going to press the dropper, right? So water comes out of the dropper, and then the observation is, we know that here you would observe a fountain, but now it would be of blue color. Okay, blue colored fountain you would observe inside the flask. Okay, like this, blue colored. Clear? Now, why is this happening? Okay, let me tell you the same type of logic as that of the hydrogen chloride gas. So we know that from this experiment, we could come to know that since a small amount of water is being inserted in this round bottom flask, which is completely filled with ammonia gas. Okay, first of all, we are completely filling this with ammonia gas. That's very obvious. I think I don't need to tell you. So once the water enters into this flask, ammonia gas, okay, since it is highly soluble, that's the reason it would dissolve in this water. It would form ammonium hydroxide. Okay, but in this case, what would happen is the amount of ammonia gas inside the flask would be less, right? So the pressure inside the flask would reduce as compared to the pressure outside the flask. That's the reason the outside high pressure would push the red litmus solution into this jet tube, and this red litmus solution would be sucked up, okay, in this jet tube till that, in such a way that it would reach inside the flask and it would reach the tip of this jet tube, where it would come in contact with the ammonia gas. Okay, now this ammonia gas, we know this is basic in nature, right? So we also know that red litmus solution would turn blue, okay, when it comes in contact with the base. So that's the reason our red litmus solution is turning blue when it is coming in contact with our basic ammonia gas. Okay, and this is the reason we are observing a blue fountain. Very simple, very clear. So what we would infer from this is, since we are able to see this fountain, this means that the volume inside the amount of gas inside the flask is getting reduced. This means that the gas is getting dissolved in the water. So this means that our ammonia gas is highly soluble in water. Okay, it is very much nicely soluble in water. Okay, so now moving ahead to the chemical properties of ammonia. Now in chemical properties, we are going to study the chemical reactions which are performed by the ammonia. Okay, so first of all, we are going to start with burning of ammonia in oxygen. Okay, now very interesting reaction. Okay, first of all, let me tell you that, see, this ammonia, okay, is not the supporter of combustion. Okay, just like our oxygen is the supporter of combustion, ammonia is not the supporter of combustion. How we could come to know this? It just extinguishes burning splint. Okay, if you take a burning splint towards the to the mouth of the test tube which is having ammonia gas, it would extinguish the burning splint. Very simple. Now coming back to the point, that burning of ammonia in oxygen. So for this, I have a wide glass tube, okay, now which is having this rubber cork like thing, okay, and this rubber cork is having like two holes in it. Okay, so what I will do is, I will just make two holes like this. Okay, right, and through these two holes I'm going to pass a longer tube, okay, like this, and another one shorter tube like this. So through the shorter tube I'm going to pass oxygen, and through the longer tube I'm going to pass ammonia gas. Okay, so what we want, the burning of ammonia in oxygen, right? So after passing, I would apply the matchstick. Okay, matchstick is ignited, and then what I would observe is our ammonia would burn with this yellow flame. Okay, like this. So it would be very interesting to see this. Now you need to remember this, remember the color of the flame, right? Ammonia burns with greenish yellow flame. So what is the reaction which is taking place here? Let's see. Okay, so ammonia, it is burning in air, burning in oxygen. Okay, so the reaction is irreversible. Okay, IRR. Okay, pardon about this capital R. So reaction is irreversible. First of all, so what it would give us? Nitrogen gas and water vapor. Okay, this is water vapor. Sorry. Okay. Interesting thing about this reaction is, I have told you it is irreversible. So once you have set up this, okay, ammonia and oxygen is mixed and you just apply a matchstick, no one can stop this reaction from taking place. No one can stop the ammonia from burning, right? So you got this point. That's why, see, we say that the mixture of ammonia and oxygen is dangerous, right? It is explosive, because if you keep this mixture, okay, ready, and if you just place a matchstick, it would just burn like anything. It would just burn. Okay, so it's dangerous. The first thing. And another one interesting thing which you could figure out from this reaction is, see, ammonia is reacting with oxygen and it is producing nitrogen and hydrogen. So from this reaction, we came to know that our ammonia is made up of nitrogen, okay, and it is made up of hydrogen, right? Because nitrogen gas is evolved and water vapor is formed. So in nitrogen gas, nitrogen is there. In water vapor, there is hydrogen along with oxygen. Okay, so we know that oxygen we are taking. Okay, we are taking oxygen in reactant. What is there in ammonia, we don't know. But now we know that there is nitrogen and there is hydrogen and there is oxygen in the product. Okay, so we can come to know. So from this we came to know that our ammonia. Okay, so this oxygen is from this oxygen, right? But the rest elements would come from ammonia itself. So that's why we come to know that ammonia is made up of nitrogen and hydrogen from this reaction. Very interesting. Okay, so we have seen the combustion part. We have seen the procedure, how to carry out this reaction. We have also seen the reaction itself, the two interesting things about the reaction. And lastly, the observation which I have already told you, that ammonia burns with a greenish yellow flame. Okay, now let's see the catalytic oxidation of ammonia. Okay, we have just seen the burning of ammonia and oxygen. Now here the ammonia will get oxidized, which means ammonia and oxygen are going to react, but in the presence of catalyst. Okay, so let me tell you the simple procedure for this catalytic oxidation. What we are going to do is simply we are going to take dry oxygen, dry ammonia. Okay, we are going to pass them, okay, through this inlets first of all, and we are also going to make them, okay, pass over. You can see this platinum. Okay, so this is acting as a catalyst. Okay, and we are going to make these gases to pass over this heated platinum catalyst. Okay, heated platinum catalyst. Very interesting. Now, one more interesting thing to observe here is when the platinum is heated, na, it shows a very nice reddish glow. Okay, reddish glow. Clear? So this is the procedure. Now let's turn on to the reaction. Okay, so what happens when we are carrying out this now? So we are mixing ammonia and oxygen. Okay, so basically ammonia is reacting with oxygen here in the presence of platinum catalyst. Okay, and yes, I haven't told you, we are going to heat this to 800 degrees Celsius. Okay, and this is a combustion tube. Okay, you can note it down. So we are going to pass these gases, okay, in the combustion tube through the heated platinum catalyst. Okay, very simple, or over the heated platinum catalyst. Okay, and I have told you this is having a reddish glow. So in the reaction, ammonia and oxygen would react. Okay, they would react over this platinum catalyst, and the temperature is about 800 degrees Celsius, and it would form very interesting nitric oxide. Okay, and water vapor. Okay, water vapor. So this nitric oxide, okay, till this point I hope it would be understood to you. Now after this, simply we have to just go again through the process. So what happens to this nitric oxide then? So we allow this nitric oxide to pass through this delivery tube, right? Okay, the water droplets you can see here, they would be formed in this combustion tube. Now this nitric oxide enters into this flask. Okay, and here it reacts with oxygen. Okay, this nitric oxide, and it forms nitrogen dioxide, NO2. Now this nitrogen dioxide gas is having reddish brown color. Okay, very interesting to know. So now the reaction is done. Okay, we can get out the nitrogen dioxide gas outside from this flask. So this was all about the catalytic oxidation of ammonia. But okay, we have seen the procedure, we have seen the reaction itself. Okay, we have seen what happens to this nitric oxide, okay, when it enters the flask. Three things. But the most important thing is the observation. What you would observe here is a reddish brown gas in the flask. Okay, this is the observation, first observation. Okay, why is it forming? I have already told you. And second observation is, as I have told you, the platinum is showing the reddish glow when it is heated. Okay, but still when we stop the heating, okay, then too the platinum will glow. Okay, why is it so? Because we know that in this reaction, if I haven't told you, let me tell you, heat is also liberated, okay, in this reaction itself. So if at all we stop heating the platinum catalyst now, okay, there is enough heat here in this combustion tube which would make this platinum to glow. Okay, so this is also an interesting observation which you can see. Okay, after stopping the heat, after we stop heating, then too platinum catalyst will glow. Okay, now moving ahead to the C chemical property, which is ammonia, which is acting as reducing agent. Okay, so now let's see the magic of ammonia, like in the reactions in which it would reduce the other reagents. Okay, so first of all, it would reduce, we would see the reactions of ammonia, okay, with metallic oxides. Okay, and ammonia is now going to reduce this metallic oxides. Okay, so the condition here is very important thing, you should remember that ammonia, okay, it is passed over hot metallic oxides. Okay, so we need to heat this metallic oxides first, and then we are going to pass ammonia through this hot metallic oxides, and then the hot metallic oxides, okay, would get converted into metal. Okay, oxygen would move on with the hydrogen, okay, and it would form water vapor. Okay, so metal, oxygen, hydrogen, water vapor, and then nitrogen gas is formed. Okay, N2 is released. So this is the general reaction which you need to remember simply. Okay, now you need to apply this reaction to the two metallic oxides, okay, which we have to study in our syllabus. First is this copper 2 oxide. Now why we call it copper 2? It's very simple to know. See here, copper it's having charge 2 plus, oxygen 2 minus, right? So oxygen 2 minus, copper 2 plus, right? So 2 plus 2 minus balanced. So therefore copper CuO, copper 2 oxide. Okay, now let me erase this. So here the reaction would exactly take place in the same manner. Okay, ammonia would be passed through this hot copper 2 oxide. Okay, hot copper 2 oxide, which is having black color. Okay, so hot copper 2 oxide having black color. I have already written it in black. And what happens is copper would be formed. Okay, now the copper which is formed, it is of reddish brown color, because we know the general reaction. Okay, the ammonia gas is passed over the hot metallic oxides and it gives us metal, okay, water vapor and nitrogen gas. So metal we have got, then water vapor simply, and nitrogen gas. Okay, so the interesting thing about this reaction is they would ask you like give one observation when the ammonia is passed over hot copper 2 oxide. So what would be your observation? You won't say that copper is formed. Okay, you cannot figure out what is forming, okay, by just looking at it. You can just tell the change in the color, right? All those things which we know how to write the answer for observations. So we can write that the black copper 2 oxide, because now here we know that we are using copper 2 oxide and it is in black in color, so we can use that word that we can observe that the black copper 2 oxide is turned into reddish brown copper. Very simple. So this would be your observation. I'm not writing it again, you just make a note of it, of the observation as well. Same way we would see the action of ammonia on hot lead monoxide. Okay, so this is PbO. Now this lead monoxide is having yellow color. Okay, PbO, yellow. Okay, and we are passing ammonia through this hot lead monoxide, okay, which is yellow in color, and it would give us, it would give us lead. Okay, now I am writing it in black because I don't have gray color, but this lead is having gray color, okay, metallic lead, and rest we know that it is water and nitrogen. Okay, so this would be the reaction. Here also the observation would be the hot or the yellow lead monoxide is turned into grayish colored substance. Here also if I would have said copper, here also you would write black copper to oxide is turned into reddish brown substance. Okay, not copper. Very clear? Okay, now let's see the ammonia, which is acting as reducing agent, but the another type of reaction in which it would now act on chlorine. Okay, and it would now, since it is acting as reducing agent, it would reduce chlorine. So reduction of chlorine, okay, to HCl, okay, hydrogen chloride. So first of all, there are two conditions in which this reaction can take place between ammonia and chlorine. Okay, first one is when the ammonia is in excess. Second one is when the chlorine is in excess. We are going to see both the conditions because both the conditions are important and the reactions are quite different. Okay, so I would just divide this part. Okay, so first condition is when ammonia is in excess. Okay, so simply I would take ammonia, it reacts with chlorine. Now we know that chlorine is reduced to hydrogen chloride. That's it. So we need to fix this thing. So always chlorine is going to form hydrogen chloride. Very simple. And along with hydrogen chloride, now nitrogen gas is formed. Okay, here. But this reaction is not, but this is not the complete reaction. Okay, once the hydrogen chloride is formed, okay, this hydrogen chloride, since ammonia is in excess, right, it readily reacts with this ammonia, okay, and what it would form, you all know, ammonium chloride, right, NH4Cl. Okay, now when we would add these two reactions, then we would get the resulting reaction, which is the actual reaction which is taking place when the chlorine is reacting with excess of ammonia. Okay, so let me just cancel out the reactants, okay, and the product which are on the opposite sides of the reaction. Okay, so here in this reaction HCl was there in the reactant side, in this reaction HCl is there on the product side, so I have cancelled it. Okay, nothing is matching, ammonia, chlorine, NH4Cl, N2, nothing is matching here. Okay, so see ammonia, so there are two ammonia. Okay, then there is chlorine, okay, and then arrow N2 plus NH4Cl. So see students, this is not the balanced reaction. Okay, you need to balance it on your own. It's very simple. Okay, you can do it on your own. So we have to study these reactions only in the terms of 5 things. First is reactants, then product, then conditions, then the chemical equation, which is the balanced one, and lastly is the observation. So we have seen, see the reactants, the products, see this is the reactants, these are the products. Okay, condition that ammonia is in excess, simply equation I have told you to balance it, and then so all 4 things we have done, and then coming to observation. So in observation, whatever you would observe, that you have to write. So in this reaction you can see chlorine gas is reacting with ammonia, and we know that chlorine gas color is, just a minute, yellowish green. Okay, okay, the flame color was greenish yellow, right? Here the chlorine gas color is yellowish green. Okay, so I would just make it here yellow in this way, yellowish green. Okay, to give a feel of yellowish green. Now what is happening here, the yellowish green color of the chlorine gas, okay, would slowly and slowly disappear, right, because it is reacting with ammonia, and it disappears, and what is forming, ammonium chloride is forming, and this is, we all know, this is, when it is formed we get dense white fumes, right? So our observation, the lastly observation would be the yellowish green color of the chlorine gas disappears and dense white fumes are formed. Okay, no need to tell that ammonium chloride is formed. We cannot see by our naked eyes that it is ammonium chloride. We could only see the dense white fumes. That's it. Okay, now second condition is when chlorine is in excess. Okay, so here ammonia would now react with chlorine and the products would be now different. Okay, because this part is in excess. So Absolutely, chlorine would get reduced to HCl. That's the basic thing in this reaction. But apart from formation of HCl, okay, here you would get nitrogen trichloride. Okay, apart from the HCl, you would get nitrogen trichloride also, which is formed. And this nitrogen trichloride, okay, it's highly explosive liquid. Okay, doom. Now, interesting thing about this is, what we need to remember is, it is also yellow colored. Okay, so I have told you, see, reactants, products, condition. Okay, reactant, products, condition, then equation, you need to balance it. Okay, and then observations. So observation would be, here the yellow colored liquid is formed, right? This NCl3, yellow colored liquid is formed when the reaction is taking place. Very simple, very clear. Now, coming to the last type of reactions. Okay, now here ammonia is not going to react. Here we are going to see the reactions of aqueous solution of ammonia. Okay, now what is this aqueous solution of ammonia, or how we prepare this aqueous solution of ammonia? We simply take ammonia, okay, and we make this ammonia to just like swim in water, okay, to dissolve in water. I'm joking. Okay, so when this ammonia dissolves in water, okay, we get the aqueous solution of ammonia, which is simply what it is. See, ammonia plus water, it is simply ammonium hydroxide. Okay, NH4. Okay, so one H is remaining and O is remaining. So NH4, 1H, O, OH. Okay, ammonium hydroxide. Now, actually what we are going to see now, the reactions of ammonium hydroxide. Okay, the aqueous solution of ammonia, as I have told now, ammonium hydroxide. So simply the reactions are very easy. We have already seen these type of reactions when we were studying the chemical properties of bases in chapter acid, bases and salts. Okay, so what would happen when the base would react with acid? Okay, because ammonium hydroxide is an alkali. Okay, and alkali is also a base, right? So what would happen when a base reacts with acid? Simply it would form salt and water. So these are the simple reactions. So you can take hydrochloric. Now we have to study the reactions of ammonium hydroxide with hydrochloric acid, with nitric acid, and with sulfuric acid. Okay, so here it would simply form simple salts, means very easy salts, and water. So now which salts are formed? Let's see the acids first. So HCl, right? So Cl and NH4. So NH4Cl would be formed, okay, and H2O. Okay, H and OH, H2O simply. So ammonium chloride plus H2O. Okay, ammonium chloride plus H2O. Same way, ammonium nitrate plus HOH, H2O. Okay. Oh, here it is. NH4, NO3. Okay, and then HOH, H2O. Same way, ammonium sulfate, okay, and here ammonium sulfate, and here HOH, H2O. Ammonium sulfate, it's like this, NH4 twice SO4 plus H2O. Now you need to balance the reaction. Okay, if some of the reaction is unbalanced, you just balance it. Okay, then your job is done. So simple reactions of ammonium hydroxide with the base to give salt and water. Okay, so now the last type of reactions. Okay, the second type of the reactions of NH4OH, simply, right? Aqueous solution of ammonia means. So now here the reaction of NH4OH with the solutions of soluble metallic salts. Okay, so we are having some metallic salts which are soluble, okay, and we are making their solutions. Okay, so we are having this 5, okay, solutions of soluble metallic salts. These all metallic salts are soluble. Okay, so we can get a metallic salt solution. Clear? Now in our syllabus we need to study this only, so that's why I have taken this examples only. But let me tell you that we have already studied these reactions, okay, in analytical chemistry, chapter analytical chemistry, chapter number 4, where we have studied the reaction of ammonium hydroxide with the metallic salt solution having Fe2 plus metallic salt solution, okay, which is made up of Fe2 plus soluble salts, okay, Fe3 plus soluble salts, Pb2 plus soluble salt, Zn2 plus soluble salt, and Cu2 plus soluble salt. You can come to know that these metals in this salt are having respective charges, which I have told right now. Okay, Fe2 plus, Fe3 plus, Pb2 plus, okay, Zn2 plus, okay, here it's -1, that's why 2 minus 2 plus, same 2 plus, and then here 2 plus, simply. So their reaction was, you get precipitates, okay, which are hydroxides, okay, of the metals. So here in this case FeSO4 and NH4OH, so hydroxide would be of iron, and now since iron is in +2 state, so hydroxide would be FeOH twice, right? Clear with this? Because it is in +2, so that's why 2 OH minus ions would be required, so 2 plus 2 minus FeOH twice, right? So this would be the precipitate. Now we have also studied the color of the precipitates, okay. You need to remember that is, see, in this case FeOH twice is dirty green precipitate, okay. Clear? Now along with this, what would be formed? Ammonium salts would be formed. So see, OH and Fe is done, NH4 SO4, NH4 twice SO4, simply, okay. In the same way we would get FeOH thrice here, okay. Now I won't explain the things, we have already studied this, okay. Now this FeOH thrice is reddish brown, so I'm just making it slightly reddish brown, okay, a reddish brown precipitate. And what would be the ammonium salt formed? See, FeOH, NH4 and Cl, so NH4Cl would be formed. So you later on balance the reactions, you would get a balanced chemical equations. Same way lead hydroxide would be formed and ammonium nitrate would be formed, okay. So I would just write this lead hydroxide with black color, because we cannot use white color on the white color, because lead hydroxide precipitate is PbOH twice, it's white, okay. So lead hydroxide, and I would get the lead hydroxide and the ammonium salt, ammonium nitrate, NH4NO3. Same way zinc hydroxide, okay, would be formed, zinc hydroxide, ZnOH twice, okay, and then ammonium nitrate again. The color is gelatinous white. And nitrate, right? So ammonium nitrate. And in the same way, copper hydroxide, okay, and ammonium sulfate. So pale blue PPT. So I'm just writing it with pale blue color. Copper hydroxide, pale blue, okay. Yeah, all these are precipitates. So just show the arrow of the precipitate, okay. And along with this, what would be formed? Ammonium sulfate, NH4 twice SO4, okay, CuOH twice, NH4 twice SO4, okay. So these are the reactions. Now I have already told you the colors, okay. So reactants, then products, okay, the colors of the precipitates, and lastly solubility in excess of ammonia, okay. So just ammonium hydroxide, excess of ammonium hydroxide. So I'm just revising the things. No need to get into details, because I'm not going to go into detail in this thing, because we have studied it in very much detail, how the precipitates are soluble, insoluble, and all those things. So FeOH twice dirty green PPT, it is insoluble, okay. FeOH thrice is also insoluble, okay. Lead hydroxide is also insoluble. So out of this, only zinc hydroxide and copper hydroxide precipitates are soluble, okay. Clear with this part? Okay, now let's see some quick few questions. Now see, you can observe the questions that have been asked in your exams. I have noted this exam, okay, year on this side, okay. So you can just have a look. Write the balanced chemical equation for lab preparation of ammonia. So we have studied lab preparation of ammonia from ammonium chloride, right? So we use ammonium chloride, very fine, and we use excess of calcium hydroxide, right? So calcium hydroxide, okay, excess. So we need to write the balanced chemical equation, okay. So in this we also need to show the conditions as well, right? So reactants, these are the two reactants, this is the condition, okay. And what product we get? Calcium chloride we get, okay, the chloride salt, because here it is chloride. So calcium chloride, then ammonia and water, okay, simply ammonia and water, okay. And regarding this water only, the position should be slant of the flask, right? So yes. And now what you can do is you can just simply balance the reaction on your own, okay. No need for me to balance it, you can do it on your own, okay. So now see, some simple questions are also being asked like this. So complete the following table which refers to the industrial method for the preparation of ammonia. So I have already told you what is the industrial method, or which method is used in industries to prepare ammonia. Haber's process, right? We have studied it very extensively. So just we have to, so see, the name of the compound is ammonia, so name of the process for the production of ammonia, okay, which refers to the industrial method for the preparation of ammonia, is the name of the process, right, which is Haber's process. Okay, and the catalytic equation, so they need equation with catalyst, okay, just not the equation, simple equation. So I will just write it here, N2 plus 3H2, okay, gives 2NH3, right? So N2, 3 to the 6H, 3 to the 6H, right? So balanced. And yes, so I will just write here finely divided Fe over this arrow. You can just make it big arrow, so that would be all. Okay, this is the reaction. Let's see the next one. Write the observation for the following. So we need to write just the observation. What it is? Ammonia gas is passed over heated copper to oxide. Okay, so we know that what would happen. See, copper to oxide. Okay, when ammonia gas is passed over this heated copper to oxide, we know it is black in color. Simply, so what happens is we get metal, right? Metallic oxide is reduced, so we get metal. Here its color is reddish brown. We have studied this reaction. Okay, then water and N2, so water vapor is formed and N2 gas is released. Clear? So here what you would observe is, you need to just tell that the black copper to oxide turns into a reddish brown substance, not copper, right? Because we don't know, is it really a copper? Means we cannot see by our naked eyes that this is copper. Okay, on this substance there is nowhere written that I am Cu, right? So that's why you don't need to, no need to write that we get, or the black copper to oxide is turned into reddish brown copper, reddish brown substance. It's simply just a substance. Clear with this? The black copper to oxide turns into pink or reddish brown substance. Okay. So let's see the next one, the last one. Write a balanced chemical equation, reaction of excess ammonia, okay, with chlorine. So we need to write the balanced chemical equation for this. Okay, so what it is? Excess ammonia, okay, with chlorine. Okay, reaction of excess ammonia with chlorine. We have already studied this reaction. Okay, when ammonia is in excess, what would happen? Simply, we know that first of all, chlorine is reduced to HCl. Okay, and when it is in excess, okay, N2 gas is also formed. Okay, but this HCl now, since ammonia is in excess, it reacts with ammonia, okay, and it forms ammonium chloride. Okay, now what we do is we just write the net reaction. So cancel out HCl on the sides. Okay, you can just figure out, okay, the matching the reactant in this reaction, okay, with the products in the next reaction. Okay, if it is matching, you can cancel. So in this way, the reactants in this reaction is matching with the product in this reaction. HCl is matching. I have cancelled it. Then 2 ammonia. Okay, then Cl2. Okay, gives N2 plus NH4Cl. Right, now you balance this reaction on your own, you would get the balanced chemical equation. Clear? So friends, with this we have reached the end of this video. So I hope you would have enjoyed learning with me. You would have understood all the concepts of this ammonia, okay, which we have studied so far in this chapter. And I have tried to just to stick to the syllabus, okay, very finely, okay, not to go out of the syllabus for any of the points which you need to study for your exams right now. Okay, after some days you would go for your exams. So as you all know, LearnoHub matlab free hai par best hai. So stay tuned. We'll see in the next video with the next compounds, HNO3 and H2SO4. Till then, keep studying. Bye bye and have a great day.